Okay, in this video what I want to do is apply the skill that we've learned to draw Lewis formulas to answering a classic question in general chemistry or university level chemistry. And this has to do with the strength of different families of acids. So over here on the right side of the screen I have a family of acids starting with hypochlorous acid and then chlorous, chloric, and perchloric. And in this family of acids, the central atom in the molecule is a chlorine, and you can see that as we go from hypochlorous here at the top to perchloric at the bottom of the list, that we're systematically adding an oxygen as we step from one molecule to the next. And there's a corresponding increase in the acidity. In other words, hypochlorous acid is what we consider a weak acid, and perchloric acid is considered a strong acid. And as we go from hypochlorous to perchloric, the strength of the acid is increasing. Now, along with that trend, if we look at the conjugate base of each of these acids, and the conjugate base, I'll just put a bracket here. The conjugate base is going to be basically the extent of what's left in the molecule after we remove the hydrogen, and it's a base by definition because it can accept a proton. So the hypochlorite shown here can accept a proton to go back to its acidic form, and so on down the line here. And we see that when we compare the base strength, the strength of the conjugate base, that it follows that also follows a trend, but it follows the opposite trend that we see for the acids. So in other words, hypochlorite, so this conjugate base is a much stronger conjugate base than perchlorate, shown here. So when you look at the trend in acidity that exists for this family, going from weak acid to strong acid, you also see the correlation in the strength of the conjugate base. So weak acids have strong conjugate bases, and strong acids have weak conjugate bases. Now, the argument in many textbooks that's made to account for this is because as we go from hypochlorous acid to perchloric acid, you can see that we're adding an additional oxygen atom in each case as we go from the weakest of the acids to the strongest. And the argument goes that as we add oxygens to each subsequent molecule, we're adding an electronegative atom to the molecule. So we're increasing the numbers of electronegative atoms that are in the molecule, and this causes a general weakening of the base because of the electron withdrawing capabilities of the additional electronegative atoms. Now, that in itself accounts to some degree for the increase in acidity as we go from hypochlorous acid to perchloric acid. But there's actually more to this story, and the only way that you can see the other aspect of this is by actually drawing the structures and talking about the concept of resonance. All right, so we're going to go ahead and do that now. Now, I need to warn the viewer that in order to get the most out of what we're going to do next, you need to have fairly reasonable Lewis drawing, structure drawing skills. And so if you're pretty rusty with it, or if you haven't gone through the previous 9 or 10 videos in my playlist, You're going to need to do that to really understand the full aspect of this. And I'm going to be combining issues here. So in other words, when we draw these Lewis formulas, we're going to be drawing best structures and using formal charge to be certain of those aspects. And I'm going to have to streamline this in the interest of efficiency. So step one in the process is to count your valence electrons, which I'm going to do here quickly. So there's 14 total valence electrons in this molecule, accounting for the valence of the Cl and the oxygen and the extra electron coming in for the charge. All right, we're going to draw the skeleton structure. So in this case, we just put the Cl next to the oxygen. And this molecule is the easiest of the bunch because basically after we connect the two atoms, we just need to go in and put the remaining electrons in as unshared pairs. And there's no real funkiness with this thing. It's going to just look like this. And then we'll have our negative sign here. And you can see when you look at this molecule that we do not have any resonance structures. I'll just go ahead really quick and we'll go through and we'll count the electrons so you can see we've met the magic number. We have 2, 4, 6, 8, 10, 12, 14 electrons. So this structure is good to go, and we have an octet around each of the atoms. Now when we move to the next molecule is when we begin to see the differences due to the potential for resonance. So in this molecule we have a total, our magic number is going to be 20 electrons. And I go ahead and I'll place my atoms in such a way that we can easily get the structure. I'm going to have my Cl in the middle, it's the central atom, and go ahead and I'm going to connect. Now, in the interest of efficiency, this molecule is actually going to have at least one double bond in it. And so I'm going to go ahead and put it in. You can use formal charge to confirm what I'm doing. We're also going to have two unshared pairs of electrons on the Cl. And then to finish up, we're going to have 3 unshared pairs on the oxygen, on this left oxygen. All right, and 20 was our magic number. So let's go ahead and count. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. That's 20. This is our magic number. Now, you'll notice in this molecule that there's definitely a resonance structure available. And what that means, if I went in here and I numbered these oxygens, then we can redraw this molecule so that the double bond is, so that the double bond is on the other oxygen. So the alternative molecule would look like this one. So there's at least one equivalent structure for this. All right. Now, let's go ahead and move on to the next one. So we're going to have Clo4 minus. And the magic number in total valence for this one's going to be 26. And we'll have to move down on this a little bit so we have room. Here's my central atom. This time we're going to have 3 oxygens. Okay, and our Lewis formula is going to look like this. Make sure I get my electrons in. If you go around and you count, you're going to find 26 of them. Okay, and I think I forgot we have one unshared pair here. So now let's go ahead and confirm the electron count. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. All right, now you can see in this molecule that we're going to have, literally there's going to be 3 resonance structures. I'm going to go ahead and number these oxygens. All right, and without, in the interest of time, without going through and rewriting each one, or let's just see if we can get away with it. All right, so it's going to be Our next one's going to be like this. And maybe as a compromise, what I'll do is just leave the unshared electrons out. Let's see, here's my pair. Put that in. All right, and then this next one will look like this. The main thing to see is that keep in mind that I numbered the oxygens. So we're not just turning the molecules, the point. We're actually moving electrons around. So I'll go back in and I'll number these oxygens so you can see what's going on with it. And then this is, here's my pair of electrons. All right, and the thing is, going back here, is if you calculate your FCs on each of these CLs, the FC remains 0 in the configuration that I'm drawing the molecules. All right, and you can convince yourself of that by going through and calculating in each of these cases. All right, now the last one is Clo4 minus, and our total electron count here is 32. All right, and when we go through and we draw the structure for this one, it's going to look like this. Whoops. All right, and we're going to have our 3 unshared pairs on this one. Get these guys in there. All right, and you can see, since there are 4 oxygens on this, in this molecule, that there's going to be, literally there'll be there's going to be 4 different resonance forms for this. So I'll number my oxygens. We got 1, 2, 3, and 4. So you can draw 4 different distinct resonance structures for this one. I'm just going to do it this way, where that single bonded oxygen is going to be rotated between the 4 different oxygens. So and then again, if you go through and you calculate my FC for this, all right, it's going to be FC equal to 0. All right, and I'll do it for this molecule really quick just to make the point. So remember, your formal charge is going to be the valence electrons, and it's minus a sum, which is 1/2 of the bonding electrons. So we've got 2, 4, 6, 8, 10, 12, 14. So 1/2 of the bonding electrons plus unshared pairs. All right, and in this case, there are no unshared pairs in this molecule, so FC is going to be equal to 0. All right, now for this guy right here, let's do this one really quick. It's going to be equal to 7 minus, all right, now quantity, all right, 1/2 bonding, so it's going to be 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. So that's 5. And then notice that we've got an unshared pair for 2, so FC is equal to 0. All right, and if you keep on going with this, you'll see that FC is 0 in each of these cases. So now let's put this together. So there's 2 reasons why the acidity increases as we go from the hypochlorous acid to hypochloric acid. We've added, and I'm going to abbreviate the word electronegative atoms as we go from hypochlorous to hypochloric. Specifically, we're adding an oxygen. So these are called actually oxyacids. All right, and the second reason is that we have an increase in resonance as we go from hypochlorous to hypochloric. And what this allows us to do is to delocalize the bonding electrons that go to the proton. All right, so really quick, if we look at the perchloric example, whoops. And if we look at the perchloric acid, and we add the proton, this is what it's going to look like. All right, and when I say that the resonance helps with the delocalization, you see it's this set of electrons right here that's involved in bonding the proton. And the release of the proton, all right, which happens when water actually takes it, right? Water accepts the proton here. So when water actually takes this proton, these bonding electrons are basically delocalized into the molecule. And the reason they can delocalize is because of this resonance, because of the capability of these of the electrons involved in the multiple bond to be dispersed over the surface area of the molecule. All right, and I think I'm going to close with that.